All right, so moving along here, what we're going to do is we're going to shift our way we think about gravity now. I'm going to move it away from kind of how it was introduced in the grade 10 science, how we looked at it in the grade 11. So really in this course, we've been assuming G is 10 because I'm lazy and don't like decimals, so it just makes life easier. But now I want to talk about gravity or acceleration due to gravity. But I want to talk about it in terms of field strength instead. So what would really happen here is we take our equation, and this is Newton's second law of the unbalanced force, except we're looking at it specifically with gravity. And we're going to take our other equation, our force due to gravity. So both of these are force due to gravity equals G m1 m2 over r squared. So both are force due to gravity. This one here you used in the grade 11 course pretty much all the time. Then we did one lesson on this. So what we want to do is we want to merge them. We're going to merge those two formulas. So we know that they're equal to each other. So mg equals g m1 m2 over r squared. Oops, not r2, r squared. Now, keep in mind the mass that you used here was mass of object, right? If you're figuring out the force acting on an object, it's really our m2. So if that means that it's our m2, that would mean that our m2s would cancel out here, which would tell me that I can calculate the value of gravity by taking g m1 over r squared. All right, m1 still the source. All right, r is the distance, g is a constant. So if we look at it in terms of a vector diagram here, so I just want to take a sec, vector diagram, just to help make a connection here. Whoa, that's not spelled properly. Here's the planet Earth. And using vectors, if I'm on the surface of the Earth, gravity is pulling me toward the center of the Earth. So those vectors are larger. As I move out, the vectors get shorter with the same direction. But as I move further and further out, the force due to gravity decreases. So those vectors decrease in magnitude. And that's what that formula will calculate for us. So in fact, G is what we call gravitational field intensity. Gravitational field intensity. And we write it, or what you'll commonly see it written as, is G capital M over R squared. And that capital M, whenever you see that capital M, it is mass of source. So nothing's really changed other than the notation here. All right. So there is a formula. This is the one at the end that you want added to your formula sheet. I just want to do a quick unit analysis underneath here, because gravitational field intensity, it's the relationship between the force of attraction due to the mass of the Earth, or mass of the source, and an object. So as we get closer to the Earth, that intensity increases. And that's what I was showing with that vector diagram up there. So unit analysis here. So you're asking me, how can gm over r squared give me meters per second squared? So if we take that formula from above, gm over r squared. On the previous slide, I told you that g is Newton meters squared over kilograms squared. Mass of the Earth is in kilograms, divided by r is meters squared. So this kilogram will reduce that to an exponent of 1. Meters squared will cancel out. And we end up with Newton meters per kilogram. Sorry, meters obviously canceled out incompletely. I should have put a cross to that. That's what I messed up. Newtons per kilogram is what we end up with. Newtons per kilogram is our gravitational field intensity. All right. So if we take a 100 kilogram object, then we know that it's 100 newtons per kilogram. So that allows us to do that multiplication. So there we go. So gravitational field strength, therefore the units are newtons per kilogram. So, quick example here. Determine the gravitational field intensity for an object located 1,000 kilometers away from the Earth. So we're looking at, as soon as you see field intensity, gravitational field intensity, we're not looking for gravity, we're looking for that gravitational field intensity, which means this is the associated formula for it. So 6.67 times 10 to the negative 11. Mass of the source, well, we're talking about Earth. This information would be provided on an information sheet, and I should have handed it out already, probably in the journal package. So it has all your constants on there, so you're responsible for maintaining that sheet. And in the denominator, you need to be careful here because R is the distance from center of the source. So the center of the source to 1,000 kilometers, we can look up on the sheet that the radius of the Earth is 6.38 times 10 to the 6 meters plus 1,000 kilometers. We need to switch that to meters, multiply that by 100. So we end up with that as being our expression. All right. Oops, actually, sorry. 100,000 meters in a kilometer. That's not good. We need to add 3 zeros there. And it's squared. So make sure you can use your calculator with the scientific notation, and this will come out to be 7.3 newtons per kilogram. 7.3 newtons per kilogram. So if you're at that elevation, if you were at 1,000 kilometers above the Earth's surface, you would feel, therefore, you would feel 7.3 newtons. I'm going to write it out in words for every kilogram of mass. I guess that's kind of saying the same thing twice, but I want to emphasize that 7.3 newtons, it's going to be for every kilogram of mass that makes up yourself. All right, so as we move on then, let's talk about gravitational potential energy. Gravitational potential energy. So gravitational potential energy is defined as the energy required to change an object's distance from the center of the Earth. So, looking at the diagrams here to the right, we know that the curve is going to look something like this. All right. If I want to move my object from a distance of r1, so let's say we're at surface of the Earth for argument's sake, then it's going to take, oh, I guess my F1 and F2 are drawn in the wrong location, so let's move them. So F1 is going to be right here, just because of the way I drew it. So there's my F1. If I want to move it to a new height, or new location, so a new height, this will be my F2. So what we're doing here, gravitational potential, we need to know the difference, or the energy it takes to move it from location 1 to location 2. So to find the energy we need to find the energy required, it means we have to find the area under the curve. So if you remember back to last unit when we talked about spring energy, it was the area under the curve. Now, this is going to take calculus, and I'm not going to go into calculus. So what we have is a bit of an approximation formula here to the left. So we're going to use this formula, area equals the square root of F1 times F2 multiplied by R2 minus R1. Just as a general, I'm going to tell you it comes from calculus, and you're just going to have to accept that. So F1 and F2, what are they equal to? Well, F1 is going to be GM over R1 squared. F2 is going to be GM over R2 squared. So I'm just replacing them with the formulas on the previous page there. So that's what the forces are equal to. And then we're going to multiply that expression by R2 minus R1. Actually, and there'll be some people saying, wait a minute, that's not equal to force. We got to multiply inside that square root, so you probably can sneak this in yours. This is, we have to multiply both of these by the mass of the object. So I'm going to put m2 in there to make it a force. So I'm going back to the original equation. So m2 is common there. Or actually, it'll be squared times r2 minus r1. Really, I should have had that mass should have been in each of those equations. That's why it's m squared. I just kind of didn't write it where it should have been because I wasn't writing. I should have been using the equation for force. So, oops. So cleaning that up, that means I'm going to have g squared, m squared. I have m2 squared, and I'm going to have on the bottom r1 squared, r2 squared, multiplied by r2 minus r1. Cleaning that up, everything's squared in there. It's all multiplication, so the square root simply then becomes gm m2 over r1 r2. That's multiplied by the r2 minus r1. If I distribute that in, all right, so I distribute that term in to get rid of the brackets, we end up with, in the first one, gm m2, r2s would cancel, so it'd be r1, minus gm m2. Now the r1 would cancel, so we end up with an expression that looks like that. Taking out a common factor, we see that the g is common, m2 is common, and in the what's left over is 1 over r1 minus 1 over r2. All right, so there is our formula for the gravitational potential energy. So over here where it says therefore, formula we're going to use, gm m2 1 over r1 minus 1 over r2. And what that does is it replaces mgh. All right, so just to finish this off, that mgh we used in the grade 11 course. Okay, well, it's only valid for situations close to the Earth. All right, it doesn't extend when you start getting to much higher and higher distances. So this is going to replace your MGH. So if you want to think of it as you move through the word problems, you'd say, oh, I would just use MGH here. Well, instead of MGH, we need to now use this new formula up above. So this is the formula that's going to get added to your cheat sheet, and it's replacing MGH. So it's that potential energy, or it's the new formula for gravitational potential energy. And we'll move on or continue in the next video. So before I forget, and you're asking probably, well, what's this other graph? Well, let's talk about that graph for a second. If this is it's a comparative graph with R1 and R2. So just extending those down here, talking about potential or stored energy, the energy curve is actually a mirror image of the force curve. All right, so that's your gravitational potential energy. So as we extend out, get further from the Earth, we have less potential energy or energy due to gravity. All right, the closer and closer we are to the Earth, the increase in force of attraction, the higher the amount of energy. So more EG. So it's also a curve with X and Y axes being asymptotes. All right. There. Now we can move on to the next video.